going to do is one that will show you one of the polar versions, and that is going to be CH2O, which is actually formaldehyde. So I'll draw that out once more, not really spending a ton of time on how I'm drawing it. We'll start with the C, the H, another H, and an O. And I have to add up all of the electrons, 4 plus 2 for the hydrogens. Each hydrogen has 1 electron, and then there is 1 oxygen which has 6. When you add that up, that actually once more equals 12 electrons, which turns into 6 pairs. So I have already used 3 of those pairs. Hydrogen does not need any more electrons. It never does, just content with the 1 bond, and so I focus all the rest of those electrons on oxygen. I can put lone pairs there. It has 3, so now I've used a total of 1, 2, 3, 4, 5 pairs of electrons, and I can put my last double bond to make all 6. Now we'll once more put the electronegativities on there. Hydrogen has an electronegativity of 2.1, carbon of 2.5, and oxygen of 3.5. And this is nice because you can see how all of the electrons are going to be attracted down toward the carbon, down toward the oxygen. And so we can draw arrows going down and down through that whole thing, draw the partial charges of the oxygen having a delta negative and the hydrogens having a delta positive. So obviously this is going to be a polar molecule. Whenever I'm subtracting the electronegativities, I'm going to take a shortcut here and subtract 3.5 minus 2.1, since those are on opposite sides of the molecule. 2.1. And then I end up with a total electronegativity difference of 1.4, which puts this in a polar bond category. Since I can look over at the molecule and see that there is a negative part and a positive part to that molecule, it also is going to be a polar molecule. So that means that I know I will not be using a dispersion force to hold one formaldehyde molecule to another formaldehyde molecule, and I'll draw abbreviated versions of those in their 3-dimensional form. So because there are no lone pairs on the middle carbon atom, all 3 of those bond areas spread out to make a trigonal planar geometry where the bond angles are 120 degrees. Now, one formaldehyde molecule can possibly attract another formaldehyde molecule, so I'll draw 2 of those molecules like so. It might be easier if, wow, it's not at the correct angle. There we go. It might be easier to understand if I actually label the identities of the different parts of that, because only certain parts are going to attract other parts. So I'll put the carbons in the middle and put the hydrogens over here and the oxygen over here. Oxygen here, carbon in the middle, and hydrogens here. Since we're looking at how this formaldehyde molecule attracts this formaldehyde molecule, we also need to put in the partial charges. As we saw over here, oxygen area is going to have a partial charge of negative, and the hydrogen area is going to have a partial charge of positive. So I'll put those on all of the external atoms. And then you can see pretty clearly that as it stands, when these 2 get together, there's going to be a very natural, easy connection between the negative oxygen on one molecule and the positive hydrogen on another molecule. So I'm going to draw a connection point. This is the intermolecular bond, and I'm going to label it that this is, I'm going to label what type of bond it is. If you look up here, you can see that our 2 options are hydrogen bonds or dipole forces. How do you know which is which? Well, a hydrogen bond is just a special kind of dipole force between very strong, different electronegativities. Hydrogen and chlorine, hydrogen and nitrogen, and hydrogen and oxygen and hydrogen and fluorine. And so you can see that these two are hydrogen and oxygen, and so that actually counts as a hydrogen bond. So that is the force that holds this molecule of formaldehyde with this molecule of formaldehyde. If this were not a hydrogen, maybe this were a carbon, then that would be a dipole force. Now, one common misconception is that you need to look at the internal bonds to be able to determine between a hydrogen and a dipole bond. And someone might look at the carbon and the hydrogen or the carbon and the oxygen and say, oh, that's going to be dipole, not a hydrogen bond, because it's not hydrogen to oxygen internally. Well, that's not the case. You don't look internally, you look externally at the two different molecules. And so because the hydrogen on one molecule attracts the oxygen on the other molecule, it is a hydrogen bond.